Right. So first, let's start the lecture, and then we will discuss any concerns if you have in the later times. Okay. So in the last class, we discussed about the expectation operation, and I will discuss about what we discussed in the last class first. Yeah, so in the last week, we discussed about the mth moment of a random variable x, So the mth moment of a random variable x is given by the expectation operation of that random variable to the power of m. So we can define this as using integration. So we can define it using this integration, and we can define it for the entire, real value range. So depending on the range that you consider, you can do this integration. Then we will do the integration of x to the power m into the PDF of that variable, which is x. So I will write simple x inside here. So normally we use that specific convention all the time to define the PDF. So inside the bracket you will use simple case letters, and in the outside in the fx part you will use the uppercase or capital letters. Then since we have the integration, we will do it with respect to x. And then this is the definition of the mth moment. So this mth moment is a general function that can be used to define the other statistics of a probability distribution function. And basically we can define like mean value, right? M equals 1 is the mean value. It gives the mean value of the random variable, where we denote the mean value as the expectation operation on the random variable x. So this we denote as also mu, and likewise we can do for other m values as well, right? So x squared means another parameter or some kind of other value, like ex squared is a value. And then using ex squared, using this we can find variance. But variance is not equal to the e or expectation value of the x squared. Variance is basically e x minus mu within brackets and to the power squared actually. So variance you can find by taking the difference between the random variable and the mean value and taking the square of it, and then by taking the expectation or the average of all the values that you can find for each of the x values. So variance therefore is defined as the expectation of x minus mu squared. So this we learned about in the last class. So this variance can be defined as ex squared minus mu squared, right? So this is something that we can keep in mind when we want to do calculations and find the variance value of a a random variable x. If we want to find the random variable x, we can find, if we want to find the variance, we can find the ex squared value or the expectation of x squared, and then we can subtract it with the square of the mean value. By that, we are able to get the variance value of the x. So likewise, up to mth moment, we can define the integration, and that is basically for the regarding the moments of a random variable x. So we discussed about the moments of a random variable x, and we need to know that this is for a continuous random variable. This is for a continuous random variable, right? We can easily identify it by the integration and the, continuous integration that we are doing for a dx time duration each time over the real axis. So if we see an integration of a PDF function, then we know that we are doing the integration over a continuous random variable. So if we consider the discrete random variable, the discrete random variable's expectation value also can be written in a similar manner. We'll discuss about that now. So for the discrete random variable, the main difference is you are considering discrete values as the random variable outcomes, or the random variables values. The values of the random variable are discrete. So you will be doing the integration. You will be finding the expectation of the random variable by taking the sum of all the probabilities. So if you are going to find the expected value or the average value of a random variable x, which is a discrete random variable, then we can write that the average value of that discrete random variable, which we denote as ex, average value we denote as ex of a certain x, that we can denote as the summation of values from 1 to n. Let's say the outcomes of this random variable is up to n values. Then the expectation value can be defined as x into the probability of that x value happening. So I will denote this as xi and xi to denote the specific random outcome. Specific random outcome xi is multiplied by its probability of happening pxi. And then for n number of outcomes of that random experiment or random process, we take the product between the x and the px, and then we take the addition of all those values, and that is defined as the average value of the random variable x. So this is a discrete one. So for the discrete one, we have the summation operation here. For the continuous one, we had the integration. We had the integration in place, and we took the multiplication between x and its PDF for the probability density function, which is a continuous function. And then we took the integration over all the real values that the random variable can take. So this was for the continuous random variable. So the difference between the discrete random variable and the continuous random variable, as you can see, is basically having this summation function here, and then multiplying the random variable value xi with its probability of happening pxi. So that is regarding the random variables expectation values. So today we will discuss about other, I mean, I mean, uh, topics related to multiple random variables. I mean, before going that, I also want to mention in here now, this is the mean of x, mean of x. This is the mean of x. And since we want to find the variance of x most of the time, we need to know how to define that also. So the variance of x, we need to know. So the variance of x, if x is a discrete value, can be defined as the summation. Again, we use the summation over all the possible outcomes of that random variable. And then we take the, difference between x minus the average value. Average value, if we have it, we can write it as x bar, or mu we can write, but I will use x bar here just to show that we are considering the discrete domain, and then we multiply this with the relevant probability of xi happening if this value is also xi. So for each outcome of the random variable, or if for each value of the random variable xi, we can multiply that, we can subtract that with respect to the mean value, and we can multiply it with the corresponding probability. So by taking that value, by taking the product and taking the summation, we can find the variance of x. So that is how we can find the variance of the random variable x. If we consider the discrete domain, discrete random variables. So for discrete random variables, we define the variance like this. And then we will discuss about the multiple random variables. The multiple random variables is something that we are going to discuss basically today. So multiple random variables. So multiple random variables. Multiple random variables means, as you can, I think, understand, there are multiple random variables that are considered. Let's say, for example, we have one random variable x and another random variable y. So uh, uh, now we want to see, like, what is the um, probability density function of both of these random variables. Like if both of these random variables are present in the process that we are trying to evaluate and study, we need to know the probability density functions of each of these random variables separately. And also we want to know how these random variables will work in combination as well. In combination as well. So that is what we are trying to find in this section. So before starting that part, I want to mention, like, what is the importance of discussing about these multiple random variables. So in the real world, so in multiple random variables uh, are important, and what is the reason for that? So most of the real world signals in the world cannot be modeled by a single random variable. So most of the real world random signals, the real world random signals are a combination of random variables and therefore we cannot, I mean, model the, I mean, most of the real world signals, random signals, most of the random variables, most of the real world random signals are modeled, cannot be modeled with a single random variable, cannot be modeled with a uh, single random variable using a single random variable, right? The reason is that the processes that happen in the world are happening due to many factors. So um, so we need to take the combination of those different factors or different parameters, and then we need to evaluate some kind of event occurring. Because of that, we need to find the behavior of the process under multiple random variables. We cannot model using a single random variable, but rather but we need to use multiple random variables. So in here we used X only, random variable X. So in multiple random variables, we will be considering X, Y, Z, likewise multiple random variables. And we will define how we can mathematically define the probability density function, cumulative density function, and other statistics like mean, variance. Like we will also talk about correlation, covariance. Those statistics can be defined for the multiple random variable case. So since we already know about the probability density function, cumulative density function, I think we can start from that stage. So we can define probability density functions for these systems that are defined using multiple random variables, and then using that probability density function, we can decide, okay, what is the probability of a certain event occurring once the random variables are taking some value. We will discuss about those in the later instance. Then these multiple random variables, I mean, having the knowledge allows us to find the relationship between the multiple random variables, right? So it allows us to find the relationship between the multiple random variables that are in consideration, and find the I mean the relationship, I mean the correlation and the dependency between the different random variables, right? Relationship between the different random variables we can find by uh, by evaluating this I mean probability density functions and cumulative density functions and other statistics related to this multiple random variables behavior. So we can also do like activities such as like noise cancelling, noise modeling, and then uh, maybe noise cancelling we can do once we can find the joint statistics or the joint statistics of the multiple random variables. So joint statistics of the multiple random variables can be used to find uh, the effect of, for example, the effect of noise on a certain desired signal, right? We can find the effect of noise on a certain desired signal, and then we can maybe try to understand like how to decrease the uh, effect of noise, and how to decode the information from this noisy signal. So therefore, like noise modeling can be done by the uh, I mean by the joint joint PDF, joint CDF functions, and we can use those kind of functions, the probability density functions and cumulative density functions, to um, to help in the decoding processes, modulation processes, etc. So we can do these processes using the multiple random variable knowledge. So we want to find out the multiple random variables, and their functions. We need the probability density functions and cumulative density functions of these multiple random variables, and using those we can try to decode and gain the information of the received signal. Then we can also, have, this multiple random variables are also important in areas such as machine learning, where we use machine learning to predict certain event occurring. So most of the time, a certain random event will not only constitute of one random variable, but it is dependent on multiple random variables. So we need to consider all the different random variables and their relevant probabilities to find a certain random event occurring in the future. So therefore, machine learning, which is like a predictive algorithm, needs the probability of some event occurring. So that event probability can be found using, as I said, PDFs, CDFs, and then other parameters such as mean, variance. Likewise, by using those parameters and other functions, the machine learning algorithm needs to identify what is the probability of a certain random event occurring. So the random event can be modeled using multiple random variables, because a random event in the real world is dependent on multiple random variables. Right? I hope it is kind of okay for you. So we will discuss about the multiple random variables and their probability density functions. So we call the
Doctor, can you
yes.
please may go back
Sorry.
to previous slide? I didn't get it, the last part.
Uh,
Machine learning, what?
yeah. So you mean about the prediction?
Yeah.
So if I take a situation where I want to predict some kind of random event occurring in the future, I need to know the probability of that random event occurring uh, with respect to the different random variables. So I will try to draw this. So there could be like different random variables that we are considering, and based on those different random variables, we can define certain probability distribution or probability density function. So this should be a 3D function, but I will draw it like this, as a like a line. So using this probability density function, or PDF, which is with respect to both x and y, uh, which we call as PDF of xy, and within brackets simple xy, this function will give us the probability of some event occurring with respect to both x and y random variables. So if I'm going to use machine learning, then I need to know like what is the probability of this event occurring. Let's say whatever the event is dependent on both x and y variables, random variables, right? So the x can be maybe temperature, X can be maybe temperature, and Y can be uh, something else. It could be the number of I don't know, uh, uh, number of maybe sales or something. Let's say some person is selling something, and he's trying to understand with the weather or the daytime temperature how his stocks are getting sold. So he needs to take the variation of or he needs to take the impact of both these temperature parameter and the number of sales parameter, and then he needs to first draw this probability density function. He needs to find it by doing some random experiments, and then by the probabilities that he gets, he needs to generate this probability density function. Once he does that, then using maybe machine learning or something, we can say that like if for certain temperature, and for a certain number of sales, this is the probability of the maybe probability of the uh, probability of getting some item sold. So actually, yeah, we have to consider a certain probability of some event occurring, probability of maybe objects getting sold. So I mean, in here I can say that these parameters may be like the number of objects I have, maybe number of items uh, that I have, maybe number of items that I have. So um, uh, based on these values, I can say, okay, now with the temperature and with the number of items I have, what is the probability of that object getting sold at a certain time instance using this function? And then using machine learning, I can say, okay, in the next time instance, the probability of that item getting sold is a probability which is at this point, which is lower than the previous probability. So using that probability, I can say, okay, the probability has dropped down. So in the next time instance, your sales are going to be sold at this probability of below the previous instance. So maybe using that conclusion, maybe the seller can decide, okay, after a certain time in the day, he doesn't need to sell the item anymore. The probability of getting sold is maybe 0.3 or even lesser than that. There's not much of use in selling that item. So using the probability density function, they can decide what is going to happen in the future. If they know the time now, uh, they can find what is going to happen in the future. So, so actually, I think I have to. I think this variable should be time. I think so. If I know the time, current time, and the current temperature, using those values, I can decide what is the probability of a certain object getting sold. If I know this knowledge, I can use this to derive the future outcomes using this known function. Maybe the future might not be exactly this function, and it might not follow this exact function, but since we have developed this probability density function by considering like uh, multiple outcomes from a random experiment, or we have considered multiple random I mean we have considered the data for multiple days, and then we have taken all that data for multiple days, and we have taken the average, and that those average probability values were used to draw this or generate this probability density function. So therefore we can say for any general day, this probability density function is correct. And by using this density function, we can say the kind of the forecast of what's going to happen in the next time instance. So that is what I think we can use as for machine learning applications. So I hope it is okay for you. So I think I will discuss about the probability density functions. when we have multiple random variables. So the probability density functions once we have multiple random variables, right? Of multiple random variables, the probability density function of multiple random variables we call as joint PDF functions. Joint PDF functions. So similarly for the CDF, we have joint CDF functions. For the CDF, we have joint CDF functions. So we will learn about the PDF functions definition, and we will discuss about how we can consider the PDF function under different scenarios. So we will consider the PDF function first. So the PDF of a joint random variable, right? I mean, joint word means there are multiple random variables that we are considering. So the joint random variable, joint PDF function, the joint PDF function, which is defined for multiple random variables, is defined as the integration value, right? I will try to write it mathematically first. Before that, I think I can draw a certain figure as well. So I think it's easier to understand using CDF first. So I will try to draw the CDF first, and then I will discuss about the PDF, right? So in here we are considering the joint the joint behavior of two random variables, the joint behavior of two random variables. And in here, we can say that we know the probability of, I mean, uh, probability of each of these um, random variables. So we know the probability behavior of each of these random variables, right? So let's say like the random variables are X and Y. We we can draw the joint distribution function, the behavior of the, I mean, probability. Once both of these two random variables are considered, we can draw, let's say, like this function where the y value is within a certain range and x value is within a certain range. Let's say x value is up to 1, y value is up to 1, and then maybe minus values of y are also taken into consideration, and minus values of x are also taken into consideration. So x value ranges from 1 to minus infinity, and the y value ranges from minus infinity to plus 1. In this case, now this function, uh, yeah, so this is the basically the xy plane. So this line actually shows the range of the x and y values. So any point in here we can define using x and y values. So it's like a coordinate plane where we give the value of x and y to the certain point in the plane. So the probability of this occurring we can draw as a 3D plot. This is the 2D version, and we can draw the 3D version of this plot as a on top of this on the z axis. On the z axis, we can draw the function or the variation of the PDF on top of these random variables. So let's say this is x and y, and we can define the values of the probability in the z axis. So I think I need to use a consistent, a random variable notations here. So I will use the simple x and simple y as the x and y random variable values of the random variables. And then z axis will give the probability uh, of that joint, um, I mean, joint PDF function, right? So this will give the probability of both these x and y, uh, probability of both these x and y occurring at a certain instance. So for a certain instance where we have both the effect of x and y, we can find the relevant probability using this function, and it will be given in the z-axis value. So we can find the we can find the probability value using integration, and we can define the probability. Sorry. So yeah, we can define the probability density function using integration. So I think I mentioned to you about joint CDF. I will explain to you in a little while. Joint CDF is also related to joint PDF. I will first define the PDF, and then I will define the CDF again. So the joint PDF function I will define as the integration of the probability density function over both the regions of x and y. So we in here we have doubled integral, and we have the double integral over the real value range that we are considering. So the real value range that we are considering will depend on the values that the random variables are taking. So the range of the random variables we need to know beforehand. Anyway, like once you know those values, you can substitute them uh, as appropriate. So we will define the probability density function, joint PDF function, as this integration, where you multiply the probability density function of the joint case, with the dx and dy both. So this is the joint PDF functions definition. So the real value range in here we must define based on the ranges of x and y. So for here we have to, depending on the integration that you do first, you need to define the range of x and define the range of y. Are there any questions? And then for this, joint PDF function, this is a joint PDF function. I mean, this is the, yeah, joint PDF functions. Uh, uh, yeah. So actually, I mean, we once we want to find the probability, we need to use this integration. Joint PDF function is this one. So once I want to find a certain probability, I can use this function. So this is giving certain probability of an event occurring in the range of x and y that we are considering. So I will try to write it in this place. So the probability of a certain x value be below the capital X, and y value being below the capital Y for the random variable y. We can find using this integration, and that probability value comes once we do the integration with respect to dx and dy. So the joint PDF function is the one that is allowing us to find that probability. So once you integrate, you get the probability value. So this is basically the definition of the of using PDF function to find a probability value. right? So you can find the probability value using the join PDF function like this. And then some properties that there are basically, I mean, the properties that we discussed for the single random variable case as well. So the integration of the probability distribution function should be equal to 1, and the value of the probability density function will always remain a positive value. So this fxy, simple xy, is always going to be 0 or above 0. It's going to be a positive function. We are talking about probabilities, so this is going to be a positive 0 or positive value. The integration of this function over all the ranges of x and y will be equal to 1. So, right, we are taking the integration of all the, of the total range that we are considering, then the integration will be equal to 1, right? So actually in here, we are considering a specific region, not the entire real region. So this will be some kind of x1, x2, and then y1, y2. So the difference between this integration and this integration is that in the first integration, we are considering a specific range of x and y values. In the second integration, you are considering the entire x and y ranges that are defined for the random variable. That means we are considering each and every value that the x and y can take, and then integrating over that entire region. So if the x value ranges from minus infinity to plus infinity, we need to consider those limits. And then if y value ranges from minus infinity to plus infinity, we need to consider those values as the ranges of the x and y, and we need to take the integration over all the of the total range of x and y to find the total integration, which is equal to 1. So then we will talk about um, the the CDF, right? The CDF as well. So I will delete this. So the joint CDF function, the joint CDF function is the uh, probability that you obtain once you take the uh, integration of the probability density function up to a certain point. So the joint CDF function I can define as the joint CDF function I can define as the probability that it's going to be below the certain x value, and the probability of y being below a certain y value. So this value we can find by taking the integration of the PDF function, as I said before, over that range, right? So this one we can find by taking the integration over the range that we are considering. So I think I wrote this earlier as well. So this x and y, we can take the ranges of the x and y, and using the ranges, we can do the integration of the PDF function, and then we can find the value of the probability. Let's say this is up to y. So we do the integration and we can find the we can find the CDF value. So this one we can denote using another way. We can denote it using differentiation in this manner. So same concept. So if I consider the kind of differential form of this integration, I can write this second manner. The only difference is that they are all the same. They are both the same, but the differential form is in this manner. You don't have to remember it, but you just can keep it in your mind that uh, the probability density function, PDF alone, can be defined by using the CDF function by taking the differentiation of that CDF function with respect to the variables that are in consideration, which is X and Y in this case. So the PDF alone can be described using this equation. So where this is the CDF function. So using the CDF function, you can define the PDF standalone. So if you want to find the probability of something happening, or the probability of X being below a certain range, or Y being below a certain, value, right? So these values can be some fixed values. So if you want to find the probability of such an event occurring, which is again equivalent to finding the value of the CDF up to that point, you can use the integration that I have shown in this in here. You can use this integration to find the probability, basically. So that is about how the CDF is defined. So you can relate CDF and PDF all the time, and they are related, and we can find the probabilities using the those uh, definitions of PDF and CDF. So basically we define we use the integration of the PDF to find the probability. So right, so we have to learn and understand some more uh, instances of PDFs and CDFs. So we learned about the PDF of the joint random variables as fxy, fxy, xy. So this is the joint PDF function. So this joint PDF function is a function that varies with both these x and y random variables, right? However, like we can consider marginal PDFs. Marginal PDFs where we want to consider independent analysis of the random variable. So marginal PDFs allow us to find the uh, independent behavior of each variable. Allow us to find independent behavior of each variable. We are considering multiple random variables case. So in that case, now the random variables are almost like combined, right? In joint PDF case, we are considering multiple random variables, and this we are considering cases where both the effect of, X and Y come into place, right? So both X and Y's effects are considered. So in that case, if we want to find the behavior of one specific random variable, then we need to consider the marginal PDF. If I want to extract and study the behavior of X only, and I want to study the probability of the X occurring, right? I want to consider the marginal PDF of X, right? So, so in order for me to find the marginal PDF, I need to keep that uh, whatever the random variable fixed, and then I need to vary the other random variable. So I will explain about that. So marginal PDFs I can take in two different manners if there are two random variables. So if marginal PDF of X, I will take marginal PDF of X, I can define as the PDF that I will obtain once I will keep X as, yeah, uh, I will keep X fixed, right? And then uh, obtain the, I will vary the, I will vary the values of Y. So I will vary the values of Y, and I will obtain the PDF once I do that. So this marginal PDF of X we obtain by taking the integration of the joint PDF. I will take the integration of the joint PDF, which is with respect to X and Y, over dy axis only. Only along Y axis I do the integration. I keep the value of X fixed, right? For a certain X value, let's say X value I keep as X equals 1. And for X equals 1, I find the marginal PDF. Marginal PDF, and then I can find the value of that. I mean, I will be able to find the value once I take the integration over the y-axis. So in here, I will only consider the range of y as the integration limits. So so this is called as the marginal PDF of X. Marginal PDF of X. This is known as the marginal PDF of X, and it is used to it is basically defined where I'm changing the value of Y and I keep the value of X fixed. So X has a certain value. Let's say X is 1 and X is kept as 1, and the Y values are changed from minus infinity to plus infinity, or to the limits of Y that is defined. I mean, there could be some specific limits of Y. I can substitute those limits into this integration, and I can find the integration value that I obtain in this situation. That is known as the marginal PDF of X. Right, so marginal PDF of X is defined like this. Similarly, I can define the marginal PDF of Y. Marginal PDF of Y. I can define, how can I define the marginal PDF of Y? Right? What are the differences that are happening in the integration? Yeah, marginal PDF of Y is fixed, Y is some kind of a value. And then integration should happen with respect to what? Yeah, integration should be happening with respect to X, and integration will happen in the X axis. So the marginal PDF of Y we can define as Fy, simple Y, and the range of the values of the x which we are varying, and then we are taking the integration of the joint PDF function with respect to x only. We are taking the integration with respect to x only, and we will get the value of the marginal PDF of y at that instance. So, so this is the marginal PDF values, and similarly we can define marginal CDF values. Marginal CDF values we can define as the probability of these random variables being below certain x and y limits. So I will basically, um, I mean, basically this is once you find the PDF values, once you find the PDF values of the marginal PDF values of y. In here, we have found the marginal PDF of y. We can find the marginal CDF of y by taking the integration of this over that certain xy range, right? So basically, that is regarding the CDF. So I think I will discuss about the next sections, but I will give you a small break of 5 minutes and then we will start again. If you have any questions, I will address them during these 5 minutes.
Susan,
Yeah.
yeah. Can you do some example using that theoretical part with some question?
Yeah, today I will be doing some questions. I need to
Yeah.
first cover this content and then I will start that.
Yeah, thank you, madam.
So you have asked some questions. So um, yeah, so the module outline. You mean about the current section that I'm doing is regarding random signals and random processes, if that is what you're asking. And if you don't have LMS access, I don't know the reason of that. I have already uploaded the LMS, module outlines for both the LGMU and ECE students. The LMS separately. If possible, you can ask your friends to share it with you, right? If possible, ask them. Otherwise, you can let me know. I will share it with you. So I will continue. Regarding your question about the module outline, I will share it after today's lecture. I mean, I will do the lecture and I will share those with you during the last few minutes. So, we were discussing about the marginal PDFs and the marginal CDFs. So currently, we have discussed about the joint PDF functions in general, joint PDF function. Then we have discussed about the how it relates to the CDF, joint CDF, right? Then we discussed about the marginal PDF, and we have discussed about how it relates to the marginal CDF, how we can derive the CDF or value of the CDF based on the PDF. So basically, we have the marginal PDFs as let's say marginal PDF of marginal PDF of X. We can define as the integration of the joint PDF function over a certain range of Y, let's say, because in here I'm going to find the marginal PDF of X and I'm going to keep the X fixed. And therefore, I'm going to do the integration of the joint function with respect to Y. So similarly, for the marginal PDF of Y, I will need to take the integration of the values of over the values of X. Let's say X values are from minus infinity to plus infinity. We will take the integration over the entire range of X. So this is the marginal PDF of Y, and this is the marginal PDF of X. So similarly, the marginal CDF of X and marginal CDF of Y, I can define using these mathematical notations where I denote the limit of X, right? The limit of X that I'm considering as the fixed X value here, right? So in here, I'm considering fixed values for X when I'm considering the marginal PDF of X. So in that case, whatever the fixed value of X I will consider here when I'm trying to find the marginal CDF of X, and then I consider that the Y value changes from minus infinity to plus infinity. So I will take the limit of Y therefore as infinity, and it can be mathematically written and modeled as the situation where we have the X value below a certain fixed X value and the Y value is changing. Y value is Y value is changing. Y value is changing until infinity. So similarly, for the marginal CDF of Y, I'm considering a fixed value of Y, and up to that point, I'm doing the integration of the PDF function, and that integration will give me the probability of the X value being up to the point of infinity and the Y value being below a certain Y value being below a certain fixed Y value. So this is basically the mathematical definition of the CDF marginal CDF function. Right. So since the Y value is going up to infinity, we are not considering that as a input value. We are only considering the limit up to which we are doing the integration in here. So X is fixed here, and the Y is fixed here. So we are only considering those fixed values up to which we are doing the integration of the PDF function, and then we are finding the probability of that variable happening, the probability of that event occurring in this condition, in this case. So these are the mathematical definitions, and then we will use these things in some examples and we will try to understand how it works. So I'm just giving the mathematical explanations first because I think without defining them, I cannot use them. Then I need to also define the conditional PDF and the conditional CDF. So I will first consider about the conditional PDF. So in probability, you learn about the conditional probabilities, like conditional probabilities, right? So something conditional means like you have certain instance or some kind of event that had already happened in the past. Some event has already happened in the past, right? Some event already happened in the past, and then we know the probability of that happening, or we know the probability distribution of that event, and then we know the probability distribution function of that, whatever the variable or that probability of that certain event. And then using that probability, we define the probability of a certain another event happening with respect to not only one variable, but with respect to multiple variables. So the probability, conditional probability means the probability of maybe one or two more or more variables occurring. Once you know a probability of certain certain event occurring with respect to a certain single variable, let's say, right? We know a certain event occurring, we know the probability, and based on that probability, we now try to find the probability of another event occurring that that is the combination of multiple variables. And basically, and this is the basic concept about conditional probabilities. So when we are talking about uh, the the probability density functions, when we discuss about the probability density functions and how we can define the conditional probability density function, we need to know the probability density function of a certain random variable, and based on that probability density function, we can define the probability of uh, the joint. Uh, uh, we can find the probability of another event occurring using the joint PDF function. So I will give the definition of the conditional probability density function in a new slide. So the conditional probability means like you know that some event has happened, so it is defined like this. So it is defined as a fraction where you denote the event that already happened in the denominator, and then you define that probability density function like this. So f capital X over capital f y over x, and then y over x. This conditional probability of y occurring when you know x has occurred is given using this fraction where you know the joint PDF of both these variables occurring, and then you know the probability or the probability density function of one of the variables occurring. Well, once you know this and you know the joint distribution function also, you can find the probability of only y occurring once you know x has already occurred, or the event that is related to x has already happened, and then you need to find how what is the probability of y occurring in that situation. So this is regarding the conditional PDF, and we can find similar definition for the conditional CDF, where you define the conditional CDF as the integration of this integration of the probability density functions, and then by doing the integration you can find the CDF value. So basically CDF value gives the probability of this of these random variables being within a certain range that we define. So this should be capital X, and then this probability we can find by the fraction, by this fraction. So once you know this joint, now I will try to relate this to the joint PDF function, right? Joint PDF function, if you know this, you can use this to find this probability value, probability of X being below a certain limit and Y being below a certain limit. If you know the probability density function fx x, if you know this, then you can find this by integrating over the range of X, right? And then you can, by finding these values, you can find the probability of Y happening, once you know X has happened, right? The probability of Y happening below a certain limit, once you know X has happened. So something like that. So conditional means you know that something has happened and you want to find something, another event occurring based on that data. So that is basically regarding conditional random variables and marginal random variables. And basically they were regarding the joint random variables or joint PDF and CDF distributions. So I will I think define the other operations. Now I think we have to know about the operations that we can do on the multiple random variables. So we were discussing about the distributions of the multiple random variables first. Distributions of multiple random variables earlier, where we discussed about the PDFs and CDFs. So as a second part, we will now discuss about the operations that we can do on the multiple random variables. So one of the operations is the expectation operation, or taking the average expectation operation. So if we take the expectation operation on a joint random variable, or if we take the expectation operation on a distribution function, which is defined by two random variables, right? Then we can denote it mathematically like gxy into the probability density function related to xy, and we can integrate it over x and y. So we need to include the relevant regions of x and y in these integrations. And once we do that, we can define the expectation value or the average value of that. We can define the average value of that function that is defined by two random variables, right? So we will discuss this as an example. I think it would be easier to understand then. So then, I mean, I will give another definition first. So the definition is like the um, uh, I think yeah. I will try to give an example. Then I think we will be able to discuss it. before going to the, yeah, I think I have one. Yeah. So, and we can remember this as a theory, and we will now try to solve an example where we have two random variables that define a certain function. A certain function is defined by two random variables, and we want to find the expectation value uh, of that function, right? So I will write that example. So first, the first part is that there's a continuous random variable. There's a continuous random variable which we can denote as uh, theta, which I can denote as theta, which is yeah, I will denote it as theta, and this is this random variable is distributed uniformly over the range of minus pi to plus pi. So theta is a certain angle, and it is said that it is distributed uniformly over minus pi to plus pi. So if it is denoted distributed uniformly, what does it mean? Right? Is the probability constant, or uh, is it different? Is the probability constant all over the theta range, as you think? Right? If some random variable is uniformly distributed, that means, yeah, it is constant. Uh, it has a constant probability of happening all over its values. So we take the theta as the random variable. It has the values of it has the value between minus pi to plus pi, and it has a uniform distribution. That means like its probability value is constant through through all the values of theta that can be taken. The theta values can be taken between minus pi value to plus pi value. So the probability in here is known to be uniformly distributed. That means probability of getting pi is equal to the probability of getting somewhere in between pi over 4, let's say. And likewise, the probability is same for any kind of theta value, pi minus pi over 3, likewise. So the probability is equal in all these instances. So, so can you calculate the expected value of the theta value, right? So if I take, this is the PDF function, this is the PDF function. So can you calculate the expected value of the theta? Can you calculate this expected value of theta? Right? That is the problem, right? So what is the value of theta? What is the value of E theta? That is the problem. If possible, you can try to solve this and you can let me know the answer, right? You can try to let me know the answer by calculating on your own, right? In the meantime, I will use the definitions to derive this value, right? So E theta is defined as the integration, right? Integration of the PDF function, right? The integration of the, random variable into the PDF function PDF function which is defined with respect to theta, and then simple theta if I have inside the brackets. I don't have to really worry about that much. I will be doing the integration over d theta. So if I'm doing the integration over d theta, I know that the integration limits I need to define with respect to theta. So I will define it with respect to theta, and it's going to go from minus pi to plus pi. And then I do the integration, and then I need to find f theta or the PDF value I need to know. The PDF value of the theta I need to know, right? So from this figure, one thing we can understand is the probability is same, right? Or for all the theta values, in here, the value is same. What is the value that should come here? What is the value that should come here, as you understand? What is the probability value that should come here? That's what I'm asking, okay? Fxx denotes some kind of probability. It's a constant value. So how can you find that value? How can you find this value in here, the probability value? Yeah, the area, right? So what is the area of a PDF function? What is the area of a PDF function? Under the curve? Yeah, under the curve, what is the area under the curve over this range? It should be 1, right? So the area of this function over the theta range should be equal to 1, right? So I know that area I can find by taking the multiplication between the theta values and the height of this function, right? So area I can find basically either using integration or just by mathematics I can find that. Right? I can use mathematics. Then so I will write this again. I'm sorry. I will write this as f theta theta. Then f theta theta is going to be 1, right? Its integration over the d theta should be 1. So the integration should happen from minus pi to plus pi. And then the if yeah, so you can basically get the integration actually, since I'm trying to find this f theta theta, I need to consider it as a like a constant here because it has a constant probability. So since I'm taking the integration from minus pi to plus pi in here with respect to d theta, and I will be left around with 2 pi here, right? And then the integration, then by taking it to the other side, I will be able to say that f theta, simple theta, will be equal to 1 over 2 pi. Do you have any questions? This is one way of finding it, or else you can just use the mathematics to find the height of this function. I mean, you can take the area of this function under the curve. The area will basically be coming from the width into height. The height is what we are trying to find, and width into height will be equal to 1. The height will be therefore equal to 1 over width. Width is basically 2 pi. So the height is f theta, a simple theta, and it I can obtain as 1 over 2 pi. So by finding the f theta theta, I am able to find the expectation value of the theta. So expectation value of the theta I will find by substituting 1 over 2 pi in here and then integrating with respect to theta. What is the value that I will get here after doing this? Yes, sorry. I can take the constant values outside and I'm left alone with theta d theta. So once I do this, subtraction, sorry. Yeah, I have to integrate it with respect to theta, right? So that will give me theta squared over 2, and then it will be theta squared over 4 pi, and then I have to get the value of the output. Since this is theta squared, it means you're going to subtract the same thing, same thing from the other value. That means like I'm going to get 0 as the output. You can try it out on your own and you can check. So that means that the mean value of theta or the E of theta, the mean value of theta will be equal to 0. So that is basically saying that the mean value of the theta or the mean or the average value of theta in this distribution is going to be at the middle in here, and it is occurring at the origin. So basically that is the mean value. And then we were talking about the joint PDF functions. So we need to now consider a system where we consider like 2 random variables in place, and how we can find the expectation value of that random variable by I will show you like how it is defined. So how we can find parameters of a function which is defined using theta, we will discuss next. So the second part of that example is that we have to consider another random variable. Consider another random variable, let's say y, which is defined as a cos squared theta. And a is a constant. And we want to find out what is the expectation of y. What is this? So how can you find this one? Now that is the question. So I will start this answering this question by defining what expectation of y means. So expectation of y means expectation of a cos squared theta, right? Y is a cos squared theta, and I can define it using the integration a cos squared theta and over d theta. Since I know I know the values of theta, I know the range of theta, I can directly take the integration of the function y, which is very related directly to the theta, and take the average over the range of theta. By solving this, I can find the average value of y. So if we are given a certain like function which is related to a certain other variable, then we can find we can find, sorry, I think I need to input the f theta here, where I need to multiply this whatever the random variable, right? This one random variable y, which is reduced in theta into this place, and then I need to multiply with the probability density function of the theta, since I know the probability variation of theta, and then I can find the expectation value of y occurring under the ranges of theta. So I can find the values of this expectation value by taking the integration, and I will obtain a certain value for the integration. So this is one of the ways of finding the expectation value of a certain random variable. When we are trying to find the expectation value, sometimes basically you need to do the, you need to do the integration. And for doing the integration, you need to know the PDF function. You need to know the PDF function, and you need to know the random variable that you are considering. So the random variable you need to know, and the PDF value you need to know. If you know those two things, also you need to know the random variable's limits, the range of the random variable you need to know. And then once you know the range of the random variable, then you can do the integration over that range to find the integration that I have indicated here, which shows us the expected value of the certain random variable. So the expectation value gives me the average value of the certain random variable. So average value is given from the expectation operation. So this is how, like, basically expectation operation is defined. So expectation operation is very frequently something that we want to find out regarding a certain random signal. We want to know what is the average value that the signal can take. So if we are measuring some kind of a signal over a certain, if we consider a certain random signal, then if we, for example, if we know the amplitudes of that signal, we want to find out the mean amplitude of that signal. So in order to find the mean value, you had to find the expectation of that random signal. Then from that expectation, you can find the mean amplitude value of that signal. Do you have questions? If you have any questions, you can ask. So this okay. So this integration. So basically, you need to multiply the a cos squared theta with the f theta, right? And so I think I will not have enough space. I will write in here. So the integration minus pi to pi a cos squared theta into the f theta. Theta means the probability density function of the theta that we found out earlier, which is 1 over 2 pi, and then with respect to theta. And then I will take the constant values out, which will be 1 over 2 pi. And then I'm left alone with, I will take the a also out. A is a constant value. I'm left alone with the cos squared theta. And then I'm left alone with the d theta. And over the range that I'm considering, minus pi to plus pi. This is the only range of the theta. And then I need to write cos squared theta with respect to linear functions. So I will write as 1 plus cos 2 theta divided by 2. Right? And then with respect to d theta, I will integrate it. Then I will have two parts, a over 2 pi firstly I have 1 over 2 integrated with d theta, which is theta over 2, and then I will have right, minus, I will have cos 2 theta divide by 2 part, which I need to integrate, and then that will equal up to plus sine 2 theta over 2. And then I will again have another 2 in here, so I will put that also in here. So I think sine 2 theta over, I think sine 2 theta over 2 is the one that is remaining here. So I will do the integration from pi to minus pi. You can check whether my integration is okay. By doing this calculation, finally, you will get a over 2 by subtracting this first part with the second part. The first part will basically give 2 pi, right? This first part will give 2 pi, and 2 pi divided by 2, right? So it will give 2 pi divided by 2, and then a pi will be remaining, and then pi and pi will cancel out, and only a over 2 will remain. So this part, this second part, will be 0, because you will be taking the difference between sine 2 pi and then minus sine 2 pi, means you will be canceling those two out. So you can check that out. So this part will equal to 0, and then final answer, if that goes, will be a over 2. There are other questions that I want to give as well. They are also kind of mathematical, mathematical. I will anyway do that. So yeah, so EY is what we are trying to find, and it came as a over 2. So average value of y, average value of y parameter, or y variable. So average value of y is the one we are trying to find here. Average value of y. So y we initially defined as a cos squared theta, right? So if I want to find the average value of a certain function which is related to theta, I can define it as y, and then the average value of y I can find using the procedure we mentioned. I hope that is okay with you. And then I will discuss about another example if you like. I think it is also a little bit kind of the same, in the same area, where we are trying to find the expectation value of a certain random variable. Yes.
I'm sorry, ma'am.
No problem.
For theta, do we take minus phi to phi every time that we want to find the probability density function? Or for if theta, is it, are we considering minus phi to phi for theta every time that we want to find the PDF?
I mean, because in the question it was given that theta is varying between minus pi to plus pi all the time.
Okay. Okay, thank you. Yeah, got it.
Thank you. So the second example is also about finding expectation values of a certain random variable. So let's assume there's a certain exponential random variable, which is exponential random variable. It's a exponential random variable, and that random variable has an exponential distribution, and the distribution of that exponential random variable we have been given, and this exponential random variable is denoted by simple x. The values of the random variable are given by simple x, and the PDF function we have been already given, and which is equal to 0 if the values of x are certain in a certain range below 0, and if the value of x is above the 0, then it's going to be according to this function. So lambda into e to the minus lambda x. So these are the this is how we have defined the probability density function. So the values of the probability density function are available only for x values which are above the 0. So this distribution function will be in the exponential format. So you will have an exponential distribution. So if you have the random variable x, the x values will be having x values above 0 will be having a certain probability, and the probability function will look like this. It will not be along the minus values. There won't be any probability along the minus x values. So if you're asked to find the value of the expectation value of x, can you find that? The expectation value of x, how can you find it? Right? Expectation value of x, how can you find it? Expectation value is the average value of the random variable x. So expectation value you can find using the integration of the x random variable with its probability density function with respect to the dx. So since I know that x values will only range from 0 to infinity, I'm going to define the limits of x as 0 to infinity. And then I will also substitute the equation of the PDF into this integration. So x into lambda e to the minus lambda x into dx. So by solving this, I can find the value of the ex, right? So in order to solve this, you actually need to know the integration of how you can do integration in this instance. So a lambda value is a constant value. I can take the lambda value out, and I will have to deal with the integration that is remaining in here, which is x into e to the minus lambda x into dx. Okay, so I need to find the integration here. If I know the integration here, I will be able to find ex. So suppose you know the integration value of this. Suppose we are given already the integration of this kind as a help, right? Let's assume that in the question they are giving us some additional data. They're saying that an integration of a certain variable, integration of a certain variable from 0 to infinity along along the variable u, right? Along the variable u, when along the variable u, and if it is in this format, the integration happens in this format where we have u to the power n, e to the minus u, and du. Then we can find the integration as we are given that integration equals to n factorial, right? So we can consider that even in here we have a similar situation. We have a similar situation. However, like in here, we are considering the x to the power 1, right? I mean, the power that we are considering is the value of n is 1. And same behavior or same pattern is here to the rest of the function. So using those, using this help, we can substitute that this equals to this equals to situation where we have to consider the lambda. Lambda is an additional factor here. So when we consider the lambda, we have to divide the integration or the output by lambda in order to consider the effect of lambda. So anyway, like I will be able to write this integration as 1 factorial divided by lambda by taking into consideration the lambda factor. Because when I'm trying to integrate a certain exponential with respect to lambda x, then I need to divide that by lambda in order to obtain this e to the lambda x value. And then I will also have to consider I also have to consider I have to consider the lambda which is outside. Okay, so another problem is there. So I think I cannot directly take it like this. I need to make it. I need to follow certain steps to get the answer. So I need to consider. I need to obtain this. I need to simplify this, or I need to turn this integration into another dimension, or I need to turn this into u. I need to obtain. I need to do some substitution, and then I will simplify this. So I will substitute u equals lambda x in order to get the same behavior that I have in here. So by substituting u equals lambda x, I can turn this integration into the format where I have lambda, and then inside the integration, I will be converting this integration into the form where I can write the same integration in terms of u, and then u over lambda instead of x, and then e to the minus u, and then du, and divide by lambda. Du divide by lambda because of this relationship I'm considering. So with all that, finally I will be left around with 1 over lambda once I try to find the answer to this using the hint that is available to me. So I will be left with 1 over lambda. Is it clear to you? Yes, you can do the substitution of u equals lambda x, and then by substituting the answer that we already have been provided with as a hint, which is n factorial, I can substitute for this entire thing 1 factorial, and I will be left alone with some additional lambda. And then by cancelling out the lambdas and considering the 1 factorial, which is 1, I can take the answer as 1 over lambda. So that is regarding how we found the expectation of the x value. So I hope it is clear to you. So this is just the expectation value for different, different other parameters like variance or x to the power m values. You can find the expectation value. I'm not going to go through that now. I think we can do the same thing like that. I mean, we can do the integration in a similar manner for other cases where we want to find the expectation of x to the power of m. We can find the value of e of expectation of x to the power of m for by using the same method, where we will have additional x to the power of m factor in this integration. And then considering that, we will get a different answer in that situation. So I will maybe ask you to do that on your own. So I think this is enough for you to understand how it will progress for other situations. So with that, I think I will, stop discussing about the examples of the random variables and how to find the expectation of a random variable. So that is one of the important outcomes of the things that we discussed. So once we are given a certain random variable to us, we want to find the expectation value of that random variable, or we want to find another moment of this expectation. We want to find another moment of the random variable. So in that case, we need to use this kind of a method where we do the integration of the PDF function with respect to that certain variable. So that is the idea behind this exercise. So you need to know how to find the expectation of a certain random variable, right? So that, I think, is the takeaway. So once you do maybe some sums related to that, you can find how to do it. So if you have some trouble in finding the integration, I think, like, don't be concerned about it. Like if I'm giving it an exam, I will give a probability density function, that can be integrated, or else I'll give some support or some kind of hint to solve the integration. Then you can find the value of the integration. Using that, you will be able to easily find the expectation value of that random variable. So basically, our target was to find the expectation value, variance value, or any other statistic of a random variable. That is our target. So I hope it was clear to you. I think that I will give some examples for you to try on your own, and maybe you can submit it as an assignment. Then we will also discuss about other things, such as other parameters that are related to joint random variables as the next step. So in today's class, if I'm going to discuss, we started discussing about the joint random variables. So joint PDFs and joint CDFs, which we need to consider in cases where we have multiple random variables, when we have multiple random variables to consider, we need to consider joint PDF functions and joint CDF functions in order to find different statistics about the signal, or the random signal which is defined using multiple random variables, right? So the random signal that we are trying to analyze is dependent on these multiple random variables, x, y, z. Likewise, there could be multiple random variables that are used to define a certain random signal, right? And then once I know the joint PDF function and joint CDF functions, I can easily find the expectation value of the random variables. So I can find the expectation values of the random variables, and then I can find other variables. So about that, we will get into next, right? So I will give you 5 minutes. I will then start discussing about maybe the next part that we are going to cover in the lecture. And then we will also discuss about some MATLAB simulations that we can use to simulate some signals and find some data, or try to find some data regarding those signals using MATLAB. If you have any questions, you can let me know.
Question, ma'am.
Yes.
I'm sorry, I'm joining in late. Today is my first day, so
No problem.
maybe this question might have been come up first last week.
No problem.
Uh, you said something about the assignments. Are those the ones that been assessed for the exam, or the assignments would be something combination of a MATLAB simulation and a written question, or it's just for the practice for us to do?
Actually, most of the time, the assignments you need to go through that you will be assigned to prepare for the exams. I mean, the assignments that I give in the LMS in intermediate instances might affect the exam. So you need to go through all the questions that I will be giving in order to prepare for the exam. The MATLAB assignments, of course, like they will be like simulation based. So those won't be like evaluated during the exam. So they won't be evaluated during the exams. They are basically for you to complete as the lab assignment and then understand how MATLAB can be used for the signal processing tasks. So during the exam, you won't get these MATLAB tasks. MATLAB tasks you won't get for the exam.
Yeah, thank you. But what I meant was for the final result outcome, would it be based on assignments, a combination of exams and assignment marks, or is it 100% for the exam, or is it let's go with 70-30?
Yeah, so assignments will constitute certain percentage, mid exam will constitute certain percentage, and end exam will constitute another percentage. So basically, as of now, we have the standard where we have the assignment and the actually mid exam. If I'm considering it as a closed book exam, I will take it as a exam assignment. That means like if I'm giving mid exam as a project or something, then I will consider it as a assignment. If that is the case, I will consider the percentage to be maybe 20%, and then from the assignments 10%. if I'm going to go strictly with the mid-exam, then the percentage of the mid-exam is going to be higher than 20%. But most of the time, since like students are requesting me to do mid-exam multiple times, most of the time it would be like maybe I will give you a maybe assignment or project or some kind of thing that you can do for a long time duration, and then you can get the marks, and it will be evaluated. It will be it will constitute 20% of the final mark. So the assignments will constitute about 10% of the final mark. So end exam will be of 70%, and likewise it will go.
Yes, ma'am. Got it. Thank you very much. That's
Thank
lots
you
of
so much.
exams. Thank you very much.
Yeah, I think so. So if you, the mid exam, if I'm giving it as an assignment, it won't be an exam.
Oh,
Only
yeah,
the
yeah,
end
I
exam will
understand.
be a written one. Yeah.
Okay, thank you very much.
Thank you so much. As I said, you when you are preparing for the exam, you can refer the tutorials or any examples that I try in the class, and be prepared for those tutorials, examples that I try in the class, and any assignments that I give. You just need to prepare for those, and then I think you will be good enough to go for the exam, which is the written, exam at the end. The other ones will be MATLAB based, and you will be doing it in your own space. So the assignments that I will sometimes specify whether I want you to do it in groups or whether I want to do it in individual manner. So if I specify groups, you need to do that work as a group with the other members, and you can complete it like that. So I think the contribution of all the exams and the contribution of from the end exam and the assignments, I think I need to get some, I need to get some decision made by the administration, and then I will get back to you. Right? If I make some update regarding those contributions, I will get back to you. Maybe after discussing with the others, I will get back to you by next week. So most probable thing is that end exam contribution we can make it up to 60%. Right? Maybe 60%, and mid exam or mid assignment will constitute maybe 30%, and assignments will constitute for like 10%. That would be, I think, the other modification that might happen if I'm to change it. But still, the end exam will have 60% contribution. So we discussed about the joint PDF functions and joint CDF functions today. So we discussed about those distribution functions. So these distribution functions were helpful in understanding the other, uh, uh, they are useful for us to find parameters such as the expectation of the random variables. Let's say if there are two random variables in the function that we are considering as a random function, then we have to consider the expectation of exy, both under the effect of both random variables. We need to find the expectation. So once we are finding the expectation in this situation, we need to consider the joint PDF function, and we need to take the integration of the joint PDF function over the random variables that are considered. So if I take, for example, a situation of finding the expectation value, right? If I want to find the expectation value, I need to know these PDF values and CDF values. So let's say that my multiple random variables are defined using X and Y. and a certain random signal is following the function of gxy. So the function that defines the random signal is gxy, and I want to find the expectation of that gxy, or I want to find the average value of that gxy signal, right? I want to find the expectation or average value of this signal. So how can I find the expectation value? Can you let me know? Can you let me know that? Right. So without taking time, I think I will explain that, because I think we are doing the same thing all over again. So we need to just integrate the function. We need to just integrate the function using the probability density function fxy xy with respect to dy and dx. Right? So if you want to find the expectation value of a certain random signal that is defined by multiple random variables, right? We need to take the integration of that random signal over with its probability density function. This is known. This is the joint PDF function. This is known. And if we know this, we can find the probability of this random signal over a certain XY range. So then since I want to find the average value of this function, then I need to consider all the values that the X and Y can take in this integration. So using this definition, I can find the expectation value of the signal, right? Or the average value of the signal. The average value will be some kind of a value that will depict the average value of the function, or the average value of the signal that we are considering here. Apart from the expectation value, apart from finding the average value, there are other things that we want to sometimes find about these signals that are dependent on two random variables, right? So sometimes like these two random variables can be independent random variables. So these random variables could have their own separate distributions. X can have its own separate distribution, and Y can have its own separate distribution. In that case, we want to find out other other aspects related to these two signals, X and Y. So we want to find out, for example, how much of correlation is there between these between X and Y, correlation between X and Y. And we want to find the covariance between X and Y, right? So we want to find correlation between X and Y, and then we want to find covariance of X and Y. So correlation basically means like it is a parameter used to measure the similarity between X and Y random variables. The similarity between the signals of X and Y random variables. So the correlation function is used to find the similarity between two signals, basically. So similarity between two, between two random signals we can find using correlation parameter. So if we have some two random signals, we sometimes come into a scenario where we want to find whether those two signals are similar or not. Some random signals, although they are random, sometimes they might show some patterns. They might show some similarity. In that case, we can find that using the correlation parameter. So such kind of parameters are defined using different, mathematical equations, right? So correlation, for example, we can define as EXY EXY, the correlation between X and Y variables. If I'm going to take the X and Y variables only, I'm going to find the correlation between X and Y variables as the integration of that X and Y variables and over the function xy into fxy inside brackets xy. So I will explain this in the, in a later instance as well. So in here, you need to input the joint PDF function of x and y, and then dy dx. So exy, this function will give the correlation value or the correlation between two random signals, how similar those two random signals are. So exy value gives how similar two random variables are. So if you know the fxy or the PDF of the joint random variables fxy, if this is known, you can find the integration by substituting the range of the x and y into this integral. So you can find the correlation if you know the PDF value of the two random variables. Okay, if you know the joint PDF value, you can find the integration. So likewise, you can find the covariance value also. The covariance value is used to define how much of similarity is there between the two the variances of the two random variables. So similarity between the variances. Covariance means like similarity between the variances, or the similarity between the variance of x and variance of y. So similarity between variance of x and similarity between the variance of x with respect to its mean, similarity of variance of x with respect to its mean mu, let's say, and the variance of y with respect to its own mean, which could be another mu. So anyway, so you are going to compare two variances of x and y, and then you are going to say how much of similarity is there between those two variants. So we will discuss about those parameters in the next class. So this is like an introduction to these parameters. I will explain the definitions and the kind of the meanings of those parameters in detail. So now I think we will go into the MATLAB simulations, and we will see how we can, we can see some kind of explanation about the correlation using the MATLAB simulations. If you have any questions up to now, you can ask. So I hope you are able to see the MATLAB window. So we have another example that we are going to try to study today. So this is about signals that we are able to obtain from sensors that we place across a bridge. Let's say we place some sensors across a bridge, and we take the measurements from those sensors. The sensors will basically measure the vibrations that it has received at each point in the bridge. Let's say right at the bridge, the vibration at the bridge at 3 different points. However, like say if a certain vehicle is going, the vibration signals that you can achieve are in this format. So these sensor data are located in this this variable called sensor data. First, you need to load that data into this space. So by running this, I can load that data into the workspace. So hopefully I will have the sensor data in my in my workspace. So I need to first run this, then I will be able to get that data. So I think I'm having that data already. There's no error coming. And then I will go to yeah, I need to just run and see. Okay, think I will go to the Signal Analyzer app. So Signal Analyzer app, and then I will try to plot, see these signals there. So in here, right, I think mainly because I have run that code before, I mean, I don't have the initial sensor data variable in this region. I already have it stored in the workspace, right? So S1, S2, S3 are the sensor data that that have been collected regarding this scenario. So S1, S2, S3 are vibration data, and I have those data in my other signal analyzer app as well. So so I can see that I can see S1, S2, S3, and then I can put them over into this plot in this place. I can plot all these all these three signals, and I can obtain the kind of the pattern of those signals. These are the three signals that I have taken. So I hope that you can remember we have discussed about correlated signals. Correlated signals means there are some relationship between those signals, right? There's some kind of a similarity between those signals. So correlation means how, I mean, in simple terms, like how similar those signals are. And we are trying to find some kind of pattern between these similar signals. So these three signals that we have here are basically like correlated signals, right? The reason is that we are taking the same measurement of vibration from the sensors. The sensors are placed in different locations, but the kind of the same signal or similar signal must be received at each of the sensors, right? I hope you agree with that. Okay, so the vibration signals that we can measure, even if they are placed in different places, the signals will be quite similar to each other. But the actual values are not exactly same, but there are some similarities between these three signals. So I mean the amplitudes, the variation of the amplitudes can be within certain range, and the peaks can occur at certain time instances. So the sensor measurements that have been taken uh, in different locations. Right? The sensors have been located in different locations. I hope you can understand that. So once we receive the signals from those sensors, there's some delay. So the delay that we observe in here, in this situation, I think this signal should be here, right? So let's say, right, yeah, let's start with the 0 point where this signal measurements start to come, and we will try to overlap in all the three signals the same thing. Sorry. This signal starts from here, basically, as I understand. So I will put it to align it with the starting point. So I have basically these three signals, and one signal is starting basically from this point where I have the 600 sample. So one thing I want to know here is that this is plotted with respect to the number of samples. So with respect to number of samples, what is the vibration level that was recognized? So likewise, I am able to see all these variations with respect to the samples. But if I want to take the variation with respect to the time, I need to be able to plot it with respect to the time. So if I want to do that, I can do that by going to the analyzing app, analyzing tab, and I can say time values in here. And then if I want to work in time values, I can say sample rate, and I can give the sample rate and starting time. So sample rate we need to know beforehand. So sample rate was defined in the initial MATLAB, uh, MATLAB code, where we were defined like 11,025 was the sampling frequency. So we need to define that as the sample rate and the starting time as 0. Then I can give this as a sample rate, starting time as 0, and then, sorry, sorry, I think I need to type it, 025. So I can't copy paste it. So you have to put the value there. Once I put that value, I will be able to get the time values, the signals with respect to time values. I need to be able to get it. So only for one I have got it, I think. With respect to time, I think I need to select all the plots and then I need to do that. So now I'm able to see that I have the x-axis as time. So with respect to the time, the plot has been adjusted now. Earlier it was samples, but now it's time. So with respect to time, I can see the amplitude of the signal. So one thing I want to know is like, what is the kind of the pattern between these two signals, so these three signals. So at what point can I observe a certain peak occurring in all these three signals? So when I take these three signals, I can see that there's some peak occurring at the end, right? So in S1, S2, there are some peaks occurring at the end of the signal. So these peaks are, right, in these peaks are occurring at the end of the signal, right? In all these signals, I can see that. That is this kind of the similarity I can see, right? So in the first parts also, you can see some, some kind of peaks occurring in the first sections of the signal. But that peak is not that much, that pattern is also actually repeating in all these three signals. But in this first instance, there is some noise in here. So in this in the first parts, I can see some similarity. So you can evaluate like how similar they are by checking the amplitude of these signals. So I can go to data cursors and I can move my cursor to these points and I can check the amplitude of these signals. I can check the amplitude of these signals. I can get the value and I can check in other plots also how it happens. So in the other plots, if I want to take the same peak, what is the value of the peak I can obtain by going into the amplitude. then I can read the amplitude here, and amplitude here is different to that. So in here the peak value is related to it is another value. So you need to try to data to that point. It's going to be 0.00. You can obtain and you can read the values appropriately by moving the data cursor over the signal. So apart from that, you can read from the time axis, and you can find the delay between the peaks occurring, right? The delay between this peak and a similar peak occurring in the other signal. You can read the time values and you can take the difference. You can say, okay, there's a delay of this much between the first signal and the second signal. So as I said before, you can go to the end part of the signal as well, and you can do the analysis for the like this end half of the signal. So end half of the signal, in there we can see high peaks than the initial signal sections. So in here we have like high peaks like of 0.0025. In here we have the maximum peak occurring at 0.0052. So likewise, we can find the maximum peak that occurs in the signals, and we can take the difference between those time instances. And you can see whether there's a delay between these signals or not. Then what I want to see is that initially, when these sensor data were taken, they they have signal measurements amplitude variations like this. So initially there have been some amplitude variations, and then some kind of like peaks are occurring. So when I take S1 and S2 signals, the first signal and the second signal, I can see that the peaks have started after a certain delay. And then for the second S2 signal, the peaks have started occurring after a different delay. The delays in the first plot and the second plot are different. So that delay we might need to find out in if we want to try to align those signals together and try to observe the pattern of the three signals together. If I want to align these three signals together, then I want to get them all into one position where the signals will start at one time instance. So in that case, we can do that by using several functions that are available in the MATLAB codes. So so in this code, what I'm trying to do is first I'm trying to plot the original signals, which are the original signals that we evaluated just now. These are the original signals. We can see that each of the signals have a different time of starting. There's a time of starting in different time. In different times, the signals are starting to give values. So anyway, because of this difference, sometimes I cannot compare these three signals quickly and easily. In order to compare them, I need to align the align the signals into one instance, or I need to align the signals to the point where the values start to come. So in order to align it, one thing I can do is I can find the delay between the two signals. So between the signals S1 and S2, I can find the delay by using the find delay function. And if I want to find the delay between S1 and S3, I can do it using this command S1, S3, and you can find the delay there. So the delay values I can find by taking the delay between these values. However, like sometimes you will get 0 if there's no delay. If there's no delay, you will get 0. However, like most of the time, you need to get a value for this, which shows us that there's some delay between the three signals. So in the third section, I'm going to try to align the signals together such that they fall into the same, same pattern, such that the three signals are starting at the same point. So I will evaluate this, and now I can see that the signals have been kind of aligned in a way such that the uh, starting point is same for all of them, and the peaks, of course, the peaks are occurring at the kind of the same point in the time, almost the same peak values, right? The peak values are starting in the same point. If I want to see, like basically the point where the peaks are occurring will be around this area. So I will be able to see all these three signals very easily using this alignment. Once I align the signals, they will be aligned to one point, and then I can evaluate these three signals, and I can check their peaks and their amplitudes after alignment. So that is basically regarding how we can, although there's a delay, we can remove the delay by aligning these three signals. Is it clear to you? So I will share the code with you, and you can try it on your own, and you can try to understand the sample simulation that's given here. If you have any questions related to the simulation, you can let me know. Okay. So I will stop the discussion for now, for today. If you have any questions, you can ask.